Hello, everyone. My name is Leo Aquino, and I'm studying mechanical engineering. And today I will be presenting the eCVT system, or the electronically continuously variable transmission system that we designed for our client, BU Baja Society of Automotive Engineers. So to talk a little bit about our clients, the BU Baja SAE team is a student organization that designs, manufactures, and competes off-road vehicles. In these competitions, they're judged on many things, including acceleration, traction, you name it. But they also receive additional points for car components that are designed in-house by students rather than purchasing off the shelf. That being said, they usually buy their transmission system. So BU Baja has requested our senior design team to design a transmission system for them, and would also like it to be electronically actuated so that they may control the device. So here you can see their car, and it's hard to tell, but here's the engine, and then here is their transmission system, right, attached to it. Before I go any further, I would like to state that my team and I knew absolutely nothing about cars nor Baja competitions. So a huge constraint was we had to take time to familiarize ourselves with the technology and existing solutions. So a transmission system in this context is simply a system that transfers power from the engine to the wheels. You can think of a bike. This is probably an example that we're all probably familiar with. The power source is the pedals here, and then that transfers the rotational power here to the wheels. So as you can see, this transmission system here, the purple chain represents what the gears look like when it's in high gear, meaning that if you want to go fast on very level surfaces, or the orange chain represents when the gears are in low gear, the low gear ratio, meaning that if you need a little more extra torque and if you're trying to go uphill per se. The problem with bikes and manual transmission in cars is that you will feel the transition between these definitive gear ratios. So a continuously variable transmission system is an automatic transmission system that can smoothly transition between a wide range of effective gear ratios. After some necessary benchmarking and research, we found out that these are the most common types of CVTs. I won't go into depth with how each of these functions, but for our purposes, we will be focusing on the pulley-based system, as the other systems are either too heavy, too complex to manufacture in the scope of a year, or simply not allowed in Baja competitions. So through a vigorous and iterative design process, this is the CVT that we designed using a computer-aided design software called SolidWorks. As you can see that this is a cross-section. This is one pulley in the pulley-based system, which requires two pulleys. So here you can see the two pulleys interacting with one another. They're actuated, meaning they can contract and expand to change the gear ratios, as you can see. Typically, pulley-based systems are mechanical, so they're actuated, meaning they expand or contract using weights and centripetal force. Our design actuates the pulley electronically, and we achieve this by incorporating a lead screw and a motor. So as you can see here, this lead screw will turn, effectively pushing or pulling this whole component to actuate these sheaves. The challenge here was to design a device that could function the way we wanted it to, but at the same time, we had to consider the manufacturability of the device as a whole, as well as all the forces at play. So as you can see, there are actually many bodies and components included in the cross-section of the design. Through consultation meetings with machinists at BU machine shop Epic, it was later found out that BU actually does not have the equipment or machinery needed to properly manufacture the sheaves or the wheels here. Because of this, we had a major pivot towards a 3D printed model. Here are the images in CAD of the model, which shows the primary here and the secondary pulleys and the motors shown here that actuate them. Now, we're really proud of this conglomeration of materials. As mentioned, most of these components were 3D printed, but we do have aluminum, carbon steel, and brass components incorporated into the working model as well. We needed some of these components to be lightweight, others to endure large amounts of stress, and we even needed to consider galvanic corrosion at some point. In order to assemble the model, just as the actual device would be assembled, we utilized the intended screws, as you can see here, along with threaded heat set inserts, as shown here. Doing this allows us to simulate the manufacturability of the device, as well as making the device modular, disassembling it in order to replace any broken or outdated parts. So here you can see the current prototype of our device. As you can see, it is fully assembled, and we've attached an additional stepper motor in order to simulate the power from the engine. As we built the model, we discovered that the motors have no means to recognize the absolute position, meaning how expanded or the distance between the two wheels. So we incorporated, we had to redesign all the internal components in order to incorporate a Hall effect sensor. Basically, include a magnet and a sensor, and it would detect the strength of the magnetic field so that it would tell how far apart the wheels are. We are currently finalizing the electronic actuation through testing the Arduino code and anticipating completing that this week. So a little financials here. We've spent a total of $2,200 with $1,900 coming from Kilachand funding and $300 coming from our funding as included in the course within College of Engineering. Now it sounds like a lot, but this is actually to be expected when developing a new device. For comparison, the purely standard mechanical CVT that Baja typically buys costs about $1,200. And a similar student eCVT design group at California Polytechnic State University spent about $1,400 on their mechanical aspect and then $1,000 on their electrical controls. So here are some pie charts showing the cost breakdown. And you will notice on the left, the great thing about our model is that 70% of our spending can actually be reused for either future models or the device that can be fitted in the car itself. While only 30% of our spending actually went towards our model specifically. And then here's a further detailed breakdown of what we've spent on this model. So discoveries and future steps, as I've mentioned, the manufacturability of the sheaves was an issue that caused us to pivot towards a 3D printed model. Additionally, it was discovered that the lack of a spring in the secondary pulley led to belt misalignment, which was a safety concern. If the belt misaligns too much, the wheels operating at such a high speed would start to wobble, and this could lead to mechanical failure. Therefore, our prototype, in order to operate safely, operates at a limited effective gear ratio range. This project was great for exploring the process of additive manufacturing or 3D printing as a means to prototype complex modular devices. And we've documented all of these discoveries and will pass these, along with all of our supplies, to future engineering teams that will work on this device. Here is a list of our acknowledgements. We'd like to say that without the support from these people, our project simply would not have been possible. And with that, I would like to thank you all for joining me today and allowing me to share this project. I would like to open the floor for any questions.